Welcome to The Explainer. Today we're going to do something pretty wild. We're going on a journey to the absolute core of, well, reality itself. We're talking about the fundamental building block of everything you see, touch, and are, the atom.
All right, so let's just jump right in with a massive question. What is everything you see around you really made of? That chair you're on? The air you're breathing right now? You yourself? What's the base ingredient? It's a huge mystery that scientists have chipped away at for centuries. And trust me, the answer is smaller than you can possibly imagine.
Okay, so our story kicks off way back in the 1800s. This is where we get the first real scientific theory of the atom. And it was a simple, kind of elegant idea, really. It just pictured the atom as this tiny, completely unbreakable block.
So in the early 1800s, this guy named John Dalton comes along, and he proposes this really powerful idea. He said, okay, everything is made of these tiny, solid, totally indivisible spheres. You can kind of picture them like microscopic billiard balls, right? And this theory, it was a total game changer. But, and this is a big but, it turned out to be just the very first clue in a much, much deeper mystery.
All right, so this is where things get really interesting, because, it didn't take long for scientists to start finding some cracks in that unbreakable idea. They started finding evidence that Dalton's atom could in fact be broken apart into even smaller pieces.
And what they found inside this supposedly solid little sphere was a whole new world. Seriously. First, you have J.J. Thomson in 1897 discovering this tiny, negatively charged particle, the electron. Then, a bit later, we get the discovery of the heavy, positive proton and the neutral neutron. And these two were packed right together in the atom's core.
So look, knowing these little particles existed, that was one thing. But figuring out how they all fit together, that kicked off a massive scientific race. And our understanding just exploded. It evolved so incredibly fast. We're talking about just a few decades where the model of the atom was completely flipped on its head again and again.
The very first real attempt to, draw a picture of this new atom came from J.J. Thomson himself. He proposed what we now famously call the plum pudding model. Just picture it, a big ball of positive pudding, or dough, with these little negative electrons just stuck in there, kind of like raisins or, chocolate chips. It was a pretty good first guess, but a totally groundbreaking experiment was right around the corner, and it was about to just blow that theory out of the water.
So this physicist, Ernest Rutherford, he sets up this experiment that is now legendary. The setup was pretty simple. He takes a super thin sheet of gold foil. Then he basically fires a beam of tiny positive particles, alpha particles, right at it. Now, if the plum pudding model was right, those particles should have just sailed straight through. But that is not what happened. Most of them did go through, but some of them, and this was the shocking part, bounced almost straight back.
And that changed everything. Rutherford realized there was only one way a positive particle could bounce back like that. It had to have hit something small, really dense, and also positively charged. And this led to a totally revolutionary conclusion. The atom wasn't some soft pudding at all. It was actually mostly empty space, with this tiny, incredibly dense core right at the center, which he named the nucleus.
Now, Rutherford's model was a huge leap forward, but it created a brand new and pretty fatal puzzle. See, according to the physics they understood back then, opposite charges attract, right? Positive and negative pull together. So why didn't the negative electrons just spiral right into that positive nucleus and cause the whole atom to just collapse? His model, as great as it was, just wasn't stable. It shouldn't have been able to exist.
So how do you solve that? Well, fixing this huge stability problem was going to require another brilliant leap of imagination. And this next step, it's the one that finally gave us that iconic model of the atom that we all probably recognize today.
The solution, as it turns out, came from this Danish physicist, Niels Bohr, back in 1913. And he made a really radical suggestion. He said, what if electrons aren't actually allowed to be just anywhere around the nucleus? What if they could only exist in very specific fixed orbits, these energy levels, kind of like planets locked into their orbits around the sun? And this whole idea, it came with a brand new set of rules for how atoms work. In Bohr's model, as long as an electron is just chilling in its designated energy shell, it doesn't lose any energy. It can't, and that means it won't spiral into the nucleus.
This was a completely revolutionary concept, and it finally explained why atoms and, the entire world they build are actually stable.
Okay, so we've got a stable atom. Phew. Now the next question is, how do we tell one type of atom from another? Like, what makes a carbon atom different from an oxygen atom? Well, it all comes down to its unique identity card, so to speak.
Turns out, every single atom's identity is basically defined by two key numbers. The first one, and this is the big one, is its atomic number. That's just a simple count of how many protons are in the nucleus. And this number, it defines everything. It tells you what element you're looking at. An atom with 6 protons is always carbon, no exceptions. The second number is the mass number, and that's just the total count of protons plus neutrons.
And this system leads to some pretty interesting variations. For instance, you can have atoms of the very same element, but with a different number of neutrons. We call these isotopes. A classic example is carbon-12 and carbon-14. Same number of protons, different number of neutrons. And then there's another fun one, isobars. These are atoms of totally different elements that just happen to have the exact same mass number, like argon-40 and calcium-40. Different elements, same total weight.
So we've gone deep into this tiny, intricate structure. But why does any of this matter? Why should you care? Well, because understanding this explains, it explains pretty much everything.
I mean it. This atomic architecture, it is the absolute foundation of all of chemistry, the whole shebang. The way an atom's electrons are arranged, especially those in the outermost shell, that dictates exactly how it's going to interact and bond with other atoms. It's why some elements are super reactive and others are totally stable. It's the reason we have molecules at all, from something as simple as water all the way up to something as complex as your DNA.
And get this, the entire periodic table, that master cheat sheet for the universe, it's nothing more than a beautiful, grand organization of all the elements, laid out perfectly based on their atomic number and their electron structure. All those patterns you see in the table, they directly reflect the atomic rules we've just been talking about.
So, we've come a long way, haven't we? From a simple, solid sphere to this complex little solar system of orbiting electrons. But the mystery doesn't just stop here. It leaves us with one final, absolutely fascinating question. If everything is made of atoms, and atoms are made of protons, neutrons, and electrons, then what are those things made of? Does it go even deeper? Just how deep does this rabbit hole of reality actually go?